When a quadratic function is written in vertex form, the vertex becomes the easiest point to find. Here's our function in vertex form, and the key pieces of it are once again the a. This is the same value of a that you'll see in other forms. It determines whether the parabola opens upwards or downwards and how wide or narrow its arms are. We'll find the vertex by looking at the values of h and k. So the vertex of a parabola, if the parabola is written in vertex form, if the function is written in vertex form, is the point hk. Of course, we know that this is a quadratic function because the highest power that x is raised to is 2. It's a little bit less obvious here since the x is tucked into the brackets, but of course if we expand, we find that we get x minus h times x minus h, and multiplying the binomials together gives us x squared minus 2xh plus h squared. So that's where we find the power of 2 when our function is written in vertex form. So while it's easy to find the vertex of a parabola if it's written in vertex form, it takes a little bit of practice to make sure we get it right. One thing I noticed right away is that while I have a positive value for k, the equation has a negative value for h. The vertex is given as positive h, positive k. So let's try this out. The first function, f of x is equal to 0.5 x plus h all squared minus 1. What are the values for h and k? Well, the xy coordinate, that is the vertex, will be -2, -1. The h value is the opposite of what we find in the equation, while the value for k has the same sign. Why does this work? Let's try it by starting with the vertex. If our function is f of x is equal to a times x minus h squared plus k, what happens when we substitute in the value hk that we just found? The value of hk in our case was -2, -1. All right, so we have f of x is equal to a times x minus our value for h, and our value for h is -2. So we have x minus -2. That's all squared, and then we add the value of k, and the value of k is -1. If we tidy this up, we get a times x plus 2 all squared minus 1. In other words, if h has a value of -2, then in our equation, we get x plus 2. If k has a value of -1, we see the same thing in our equation. So try writing the vertex for the remaining 3 functions. For g of x, the value for hk is +4, +7. For m of x, it almost looks as though we're not really writing this in vertex form. It looks like m of x is written in standard form. What we can do here is think of this as a times x minus h squared plus k, but the value of h is 0. If the value of h is 0, we get x minus 0 all squared. So that's where the x squared comes from. So for m of x, the value of hk, the value of the vertex is 0, -5. And finally, for n of x, we have a similar problem. This time we don't seem to have a value for k. That means that the value for k is 0. So hk in this case is -3, 0. The vertex sits on the x-axis. Once we know how to read the vertex when a function is written in vertex form, everything else remains very much the same. Key points for a quadratic function are still the vertex, the y-intercept, and the x-intercept. So we already looked at how we find the vertex. Let's have a quick look at how we find the y and the x-intercepts. As always, to find the y-intercept, we set x equal to 0. Say we set x equal to 0. In other words, we solve for f at 0. So to find the y-intercept of the function we're given here, f of x is equal to 2 times x minus 4 all squared minus 32, we want to solve for f of 0. So we have 2 and 0 minus 4 squared minus 32. The y-intercept does take a little bit more work here than it did in standard form. We have 2, then negative 4 squared minus 32. Negative 4 all squared is positive 16. So we find 32 minus 32, or 0. So the y-intercept for this function is the value of 0, or as a coordinate point where x is equal to 0, y is equal to 0. Now let's find the x-intercepts. To solve for the x-intercepts, set the equation equal to 0, which means that we're really setting y equal to 0. Or in function notation, f of x is being set to 0. We'll find it easier to solve for x if we convert our function to standard form, in other words, if we expand, and then either factor or use the quadratic formula. Let's try this. So we have 0 is equal to 2 times x minus 4 all squared minus 32. And now we'll have to solve for x. Essentially, we're just going to expand, but what's happening here is while we do that, we are converting to standard form. Don't forget that if x minus 4 is all raised to the power of 2, this really means we need to take the binomial and multiply it by itself twice. I'll multiply the binomials first, and then multiply the product by 2. I've skipped a step here and added the middle like terms of negative 4x and negative 4x to give negative 8x. Using distributive property now, we get 2x squared minus 16x plus 32. And we still have that negative 32 hanging off the end. The 32's will cancel, so we get 2x squared minus 16x. If you know how to factor, you can factor this expression to find the x-intercepts. If not, we now have to use the quadratic formula. One more thing I can do here is I could notice that every single term is divisible by 2, so I can simplify to get 0 is equal to x squared minus 8x. But you can absolutely use the values given previously. All right, so if we need to use the quadratic formula, we need to know the values for a, b, and c. We're in standard form, so the coefficient for x squared is the value for a, and the coefficient for x is our value of b. So a has a value of 2, b has a value of negative 16, and c, and we don't see a constant here, so c has a value of 0. Let's write out the quadratic formula one more time. We are going to solve for x by evaluating negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So in our case, we have x is equal to negative 16 plus or minus the square root of negative 16 squared minus 4 times 2 times 0. All of that is divided by 2 times 2. So x is equal to 16 plus or minus the square root of negative 16 squared minus 0. In other words, the square root of 16 squared, which is just 16, all divided by 4. Therefore, x is equal to 16 plus 16 over 4, or x is equal to 16 minus 16 over 4. So x is equal to 32 divided by 4, or 8, or x is equal to 16 minus 16 is 0, 0 divided by 4 is 0. So the x-intercepts, written as coordinate points, are the points 8, 0, and 0, 0. So we found the y-intercepts and the roots, or the x-intercept, for our given function. Alternately, if you prefer to solve the equation in the way we've written it, you don't need to first convert it to standard form and then use the quadratic formula. Here's what that looks like. The goal here, as before, is to isolate x. What I do notice is that in the form it's currently written, it looks like there's only one term with an x in it. So let's isolate this binomial that we find the x in, and then use that to isolate the term with x. So first we'll add 32 to both sides. So we have 0 plus 32 is equal to 2 times x minus 4 all squared. Or just 32 is equal to 2 times x minus 4 squared. To remove the 2 from the right-hand side, we can divide both sides by 2. 2 divided by 2 eliminates it from the right-hand side, and we're left with 16 on the left-hand side. So 16 is equal to x minus 4 all squared. To undo the squaring of the binomial, we're going to take the square root of both sides. The square root of the left-hand side and the square root of the right-hand side. On the right-hand side, this leaves us with x minus 4. On the left-hand side, the square root of 16 is 4. To explicitly consider two answers, we are going to write down the fact that both positive 4 and negative 4 are solutions to the question, what is the square root of 16? Finally now, we're going to add 4 to both sides to finish isolating x. That leaves us plus or minus 4 plus 4. What does that look like? So really we've got x is equal to 4 plus or minus 4. Just to rewrite the equation one more time. In other words, x is equal to 4 plus 4, or x is equal to 4 minus 4. So x is equal to 8, or x is equal to 0. This is exactly what we found when we first tackled this problem by converting to standard form and then using the quadratic formula.